personally.
Thank you.
But yeah, let's wait until this madness with the virus somehow disappears to some normal level. Okay, so I will introduce Javier, because we used to work together for a few years. So this is Javier's first talk since he has become an IACS affiliate at the beginning of this year.
Thank you.
So I guess he's fulfilling his duty as an affiliate. Javier is an old buddy of IACS. We have known him since the summer of 2014, when he stayed at IACS for the summer, finishing his PhD thesis on the laser effect in the ion atom cohesions, which he defended with high honors in 2015 at Universidad Nacional Autónoma de México. Did I pronounce it well?
Yes, perfect. I know you can pronounce very well.
That's known as the UNAM, okay, that university.
Yeah.
And he came to IACS as my postdoc in 2015, founded by CONACYT Research Fellowship, and which is a Mexican analog to National Science Foundation, I guess. And he stayed with us for 2 years, working on plasma material surface interaction for nuclear fusion. So we all remember him as the one who would first come last go from IACS, often sleeping in IACS, irrespectively whether it was a work day, weekend, or holiday. Even worse, he made me working with him a few hours daily.
Yeah, it was my fault, sorry.
Okay, apology accepted. So such hard work definitely resulted in winning a highly prestigious German von Humboldt Research Fellowship, where he spent 2 years till 2020 in Max Planck Institute for Plasma Physics, working with Dr. Udo von Thuessan on application of machine learning for development of interatomic potentials in transition metals. He is now a staff scientist in NOMATEN Center of Excellence in Poland, and adjunct professor at National Center for Nuclear Research in Poland, where he works on numerical modeling and experiments of nanoindentation of high entropy alloys. And I guess this is the subject of his talk today. So, Jeroen, the board is yours.
Thank you so much, Professor, for this introduction and for your kind words. So I only would like to know if everybody can see my screen.
I can.
Can you see my screen?
Yep.
Yes.
Yep. Yeah.
Okay. Another question that I want to make sure if my friends, my experimentalist friends are here. Yeah, okay, I can see you, Kasia and Lucas. Welcome. I hope you are not going to be bored. So,
will you speak in Polish?
Tak.
Hello, everybody. Good luck.
This
Good luck,
is
Javier.
this is the guy who can make everything possible in the experiments. Nanoindentation, and Kasia, an outstanding experimentalist, also making everything possible for us. So let me introduce Professor Lucas Kurpaska, who is working in the National Laboratory. He really knows everything about nanoindentation. And thank you, Lucas, for being here.
Okay, nice to meet you, Lucas.
Nice to meet you all. Thank you. Thank you for invitation, and I'm looking forward to this presentation.
Okay, Javier, you can start.
Thank you so much. So, I believe everybody can see my screen, right? So today I'm going to talk about the work that we have been carrying out in the NOMATEN Center of Excellence in the National Center for Nuclear Research in Poland. And here I'm going to talk about the nanoindentation and the back-to-back work between the experiments and atomistic modeling to try to understand the mechanical nanoindentation response of the so-called medium entropy alloys. So here we would like to have materials with optimal mechanical properties for applications in extreme operating conditions. So something that we call high entropy alloys. For example, in this image, in this inset, I can show a prismatic dislocation loop that I'm going to talk about more a little bit, this kind of geometries that we can find in a plastic deformation region of some metals. This is the prismatic dislocation loop, and all of these colored atoms is the high entropy alloy of the complexity chemistry that one can see in a metal alloy. Here you can see a mixture of nickel, copper, chromium, iron, and manganese, and the well-identified dislocation loops, Shockley partials, here junctions, and corresponding Borger vectors that one can see in the plastic region when we are performing the nanoindentations. They also can be seen in the numerical modeling, and they also can be seen in the experiments by my friends by doing TEM images and this kind of things. This work is in collaboration with the group led by Professor Lucas Kurpaska, that you already met. And thank you so much for being here. And as I said, outstanding experimentalist Kasia Mulewska. She knows practically everything. It's impressive the things that she's doing. Professor Jacek Jagielski, Ania Kosińska, and also the group of Miko Alaba, where Rene Alvarez is the expert of ball metallic glasses in our group. And that's the reason that we are able to perform such simulations for high entropy alloys. And we also have the collaboration through Professor Lucas Kurpaska with Dr. Jan Zan from Oak Ridge National Laboratory, where some of the high entropy alloys are developed. So what is the motivation of work? In Oak Ridge, it has been synthesized and created the so-called single-phase concentrated solid solution alloys, or SP-CSAs, as we would like to refer to. These materials present or dream that they have optimal mechanical properties for application in extreme operating conditions and applications in energy industries on aerospace. And everybody knows that we need to have energy for everything. Only to having this presentation here, and we are in different parts of the planet, and we need energy to have all of this kind of work and also to have fun. We would like to travel. We need special materials to design all of these wonderful devices that we need to survive and to have a pleasant life in this planet. So how can we do this? We need materials that present really optimal mechanical properties, so that's high yield strength, high thermal stability, hardness. So we are really highly demanding to do these materials. We also would like to have a material with high temperature strength, good wear, fatigue resistance, excellent corrosion resistance, resistance to radiation, and that they also can work at high temperatures. So we are really demanding a lot of things for this kind of materials. So common alloys cannot provide this or cannot have this kind of mechanical material at such properties that we are needing. So I don't know if everybody is in material science. I'm going to try to explain everything, but more or less the fundaments to go in this talk step by step, because maybe some of you are, I remember that IACS is really interdisciplinary institute, and I'm going to go step by step to present what is the kind of work that we are doing here in NCBJ. So here the thing that we need is a high entropy alloy or a medium entropy alloy that we are calling it, by mixing many elements to create a material. It can be formed by 3 elements, the so-called medium entropy alloy, or 5 elements, so-called high entropy alloy. But the single phase concentrated solid solution has a special property that it can be tunable levels of lattice distortion and its chemical complexity. This is a new family of metal alloys that we are interested in, and we need to test to see if, to verify if we already reached the optimal mechanical properties. As I said, I'm not the experimentalist, so if you have questions, my friends are here. Thank you so much. So in the nanoindentation test in the experiment, how they are preparing the materials, the SP-CSA, the sample preparation is as follows. They have a single crystal were grown by using a floating zone directional solidification method from the polycrystalline drop cast ingots. Then the single crystal is oriented to the 100 surface using backscattering diffraction. This information of the 001 crystal orientation is very important for the numerical modeling. Sometimes we are dealing with this information to know where is the crystal orientation to perform the MD simulations. But this is really important. The materials that we have here and then the results that I'm going to present, it's only for the 001 crystal orientation for the experiments and for the numerical modeling. So the next step is all the study samples were carefully mechanically and electrochemically polished. Thank you so much, Kasia. I know this is too much. And here I'm presenting the results that they are obtaining from the experiments when they are doing the nanoindentation. They have this typical graph that is called the load displacement curve. And here we are going to have all the information about the mechanical properties of the material. And really, by doing nanoindentation test in these materials is a non-invasive technique. And if you are doing tensile, something is really invasive and destructive. If you are doing nanoindentation, it's better to do it to test the mechanical properties. It has some advantages and disadvantages over tensile test, but it is a good way to test the mechanical properties of a material. And with this so-called load displacement curve, one even can track the experiment, how you are doing the loading process of the Berkovich tip. This is a Berkovich tip. And in the experiments, they are using a diamond-based Berkovich indenter tip to perform the simulations, to perform the nanoindentation test. They are loading, and then they are doing the unloading. This is a SEM image that they can see from the surface target. This is nickel, and then they can visualize perfectly the mark of the indenter on the surface. And then you can see here the loading process, the maximum indentation depth that they are reaching, and then the unloading process. And here is the recovery of the material. I'm going to explain a little bit more how to read this kind of graphs for the MD simulations. As most of you know, I studied with Professor Preda, and he always told me, you need to prepare very well the samples. If you don't prepare the samples very well for them, the simulations, nothing works. So we are going to spend really some time to prepare the samples to perform the MD simulations. Why? Because if we are going to study nickel-based metal alloys, it's so easy to start with nickel. It's only one element. It's oriented to the 001 crystal orientation. We have all the tools, the numerical, the codes, and MD simulations are performed by using lamps, the large scale atomic molecular massive parallel simulator. And also we have one restriction. The better the interatomic potentials are, the better the molecular dynamic simulations will be. So here we are using the reported interatomic potentials developed by Choi et al., which are based in the second nearest neighbor EMM. They are fit to experimental data, and they have been tested by your friend René, who is an expert in ball metallic glasses, and he has been calculating all the thermodynamic properties of the high entropy alloys by using these potentials, and he's really sure that everything, the mixing entropy, everything has a good agreement with the experimental data reported in the literature. So we're really sure, and I also use these interatomic potentials to compute and to verify by myself, of course, the elastic constants of these materials, the stacking fold energy, and the surface energy, I have a good agreement with the reported paper by Choi et al. And also with experimental data. So these potentials, I trust on them. So now, how to prepare the sample? Okay, so since I don't know how to prepare a ball metallic glass and this combination, then this mixture that is extreme, my friend Rene and I carry out this study to perform MD simulations with Monte Carlo. For the nickel, we are taking the original nickel sample, then we are substituting some nickel atoms by iron atoms, and we are only distributing randomly, taking this nickel atom, putting an iron atom to reach 20% of iron or 50% of iron. Then we are also preparing the other sample, which is nickel, iron, chromium. So again, you take some nickel atoms and then put iron, take nickel, put chromium, but the story doesn't end there. Now we need to make sure that this sample needs to be compared with the SP-CSA. So how we are going to do it? We are carrying out this Monte Carlo simulation too with the swapping method. So when we are doing the optimization of the sample and the swapping of the atoms, all of them need to reach this swapping needs to satisfy some restrictions in the energy and the entropy to identify and to get the sample, which is the possible metastable configuration at room temperature. So this sample is for sure the SP-SA or as close as possible as the material that they develop in the laboratory. We also are sure that the distribution, the atomic distribution of the sample on the set direction is the same. So everything needs to be created really carefully. So we spent some time to prepare the sample, and then we define the sample because we are going to do an MD simulation by using a spherical indenter. And now again, in the experiments, they are doing the experiments with a Berkovich tip. If some of you don't know what a Berkovich tip is, something like a conical, and then it has different geometries in this part. But the tip of the indenter, it has roundness. So according to the time scale and the space scale of the simulations, we can model the Berkovich tip as a spherical indenter tip. We also can, my friends in the laboratory, they also have spherical tips. It could be also really better, but we can model everything by considering the time and space scale of the simulations to the experiments. So here we are going to use the MD simulations to try to understand the transition between the elastic part to the plastic deformation part, where the experimentalists cannot see that. So it's practically impossible to see that this is at the beginning of the loading process, and it's too detailed. So the MD simulations can provide a lot of information where the experimentalists cannot handle it a little bit. Probably in the future, because they are really great. So probably in the future they can see it. Here I'm presenting the size of the samples, how many atoms we have, the percentage of the atoms, everything that defines the sample. This study will be published, will be submitted very soon to Applied Surface Science. We hope so. And now you prepare the sample. Now, what is the next step? The next step is to figure out how we are going to do, or how we are going to emulate the experiment of the nanoindentation test. So now, as I said before, the Berkovich tip can be modeled by a spherical tip because this reason, the roundness of the tip, and also the negligible difference between the phase transformation regions presented by both tips at this early stage. We also performed some MD simulations for the Berkovich, and I don't see any difference. So to me, it's easier to do it with a spherical indenter tip. And we are figuring out the difference between these tips, Berkovich and spherical. But so far, I'm only presenting the spherical, the results for the spherical tip. Probably another talk if Professor Harrison invite me. Sorry for that. So now what is the next step? The next step is to define the sample here. And this is the indenter, the spherical indenter. The indenter will go in this direction to touch the sample. then it will dig deeper and deeper and deeper. So this is a spherical imaginary tip that it needs to be defined by an initial load and also an indentation rate. So all of this needs to be in good agreement with the experiment. And now we are going to apply some restrictions for the numerical modeling, where the bottom layers needs to be frozen. And the thermal, then we have a section for is the so-called thermal section, which is applied a Langevin thermostat to get rid of the heat added by the indenter tip and this interaction, this push on the sample. And then the last part is so-called dynamical atoms, where here we are going to run the MD simulation with an NVE ensemble. And because of the interaction of the indenter tip with the atoms, and also above the surface, we need to add the vacuum. Otherwise, we are not going to see the pileups here. So now, when you are defining when you are doing the performing MD simulations and doing the loading process and the unloading process, we also obtain the typical load displacement curve that also the experimentalists can obtain. So here, from the MD simulations, we can obtain many of them, and we can study all of them. And here in this part, you even can track the simulation. Here you have nothing, you have no interaction. This is only the vacuum. And then here, this is the surface. And this part here is the elastic part, the so-called elastic part of the loading process. And why we're calling the elastic part? Because it's only the interaction between the sphere and this plane. So according to the Hertz theory, we can fit this part with this expression. So it's only the interaction of the sphere with the plane, and it fits very well. Also in the experiments, when you are doing a spherical nanoindentation test with a spherical tip, it also reached to the Hertz theory. So since we're sure about this Hertz theory is the elastic part, we need to consider many things. Now, the indenter is going deeper and deeper and deeper and deeper. This is the so-called pop-in. I'm going to show later what the pop-in is, but it's only when we start the transition to the plastic region and the dislocations are being nucleated and propagated. Then here we have another pop-in here that we are being analyzed, and then we reach the maximum indentation depth, and then we are doing the unloading process. This unloading process needs to be elastic and needs to be in a really good correspondence between the elastic part at the beginning and at the end of the MD simulation. When we have this, we are going to use the Oliver-Farr method that is well known in nanoindentation application, in nanoindentation test. This is the Oliver-Farr method. We are using this definition for the lot. This HF is the mark that we have here, is the mark that is left by the indenter tip. And then we are applying fitting methods to identify this parameter, fitting parameter, and F0. Then the hardness of the material is computed as the lot divided by the contact area. And this same graph can be, this same method is applied by the experimentalist. So now we have the same process and the same way of measuring the hardness and also the Young modules of the material. So this is something like, it's great because we can understand both sides of the process. And then if you want to know more about our work, here we already published a paper in Material Science and Engineering A. In this work, we are doing an analysis of high temperature nanoindentation in molybdenum. Molybdenum, we have some experimental data from the University of Oxford, and they try to understand why molybdenum has a thermo-mechanical stability at high temperatures. And we figured out why this, who is responsible of this thermo-mechanical stability. Here in our group, we also have another expert in material science, who is Professor Stefanos Papanikolaou. And we team up and we realize why this thermostability at high temperatures with the junctions between the dislocations. I'm going to show in the next slides what is this about the junctions of the dislocations, and why this mechanism is responsible of the increase of the hardness of the material. So what are the results? As I said, in the MD simulations and in the experiments, they have the load displacement graphs, but now we need to analyze and we need to see what is the corresponding and back-to-back relationship. Now here, this is the result from the experiments. I'm going to show only for nickel and nickel iron 20 and 50%. When they are doing the nanoindentation test, then they have an initial load, and then they practically don't know where is the maximum depth. They actually can know because there is a correspondence with the initial load, but let's say that it's a little bit difficult to track, maybe not. And in the MD simulations, since we have the constant rate for the indenter tip, here we know where we are going to end up in the MD simulation. This is the maximum depth. So this here, when they are ending up in the maximum depth at the given initial load of the tip, now for nickel, you can see that you can go deeper in the material. And then when you have nickel iron with 20% of iron, now the tip under the same the parameters, it doesn't reach that the maximum depth in the sample. And when you have 50%, also it didn't do it. How can we see it in the MD simulations? Within the MD simulations, here it means that you need less force to go deeper in the sample, and then you need more atomic force to go deeper in the sample. So this is the correspondence. So here you cannot go deeper, and here you need more force in the MD simulations. So this is the correspondence that you have between the experiments and the MD simulations. And now we also are interested in the elastic recovery of the material. Here you have the unloading process, here well defined, and everything here for the mark. And also in the MD simulations, you have the unloading process and the elastic recovery of the material. And even here we have the pop out, and also the pop out here. This is something that we figure out in the daily discussions between experimentalists and theoreticians, that sometimes is really fantastic to discuss. These discussions are so great, so great. So we have more results. Now we need to have another correspondence between the experimental data and the MD simulations. So now in the experiments, they can calculate the hardness as a function of the indenter displacement. And the reported result is that nickel is really soft. And then when you are adding nickel and chromium to the sample, the hardness value of the material increases. You found that in the experiments, very nice. But we also found it in the MD simulations. You can see here we have this correspondent. Of course, this is the time scale for the length scale for the experiments, and this is the length scale for the MD simulations. But you can see this bump here and this bump here, and then the decreasing of the hardness as a function of the indenter displacement. And you also can see it here for the nickel, iron, chromium. And then for the other material, it is the same, this constant and this correspondence, and also here and here for nickel. So something that I forget to tell you all is that for nickel, it's only one element, and it's the crystal orientation in the 001 orientation. But since you have the symmetry and it's based on a FACC unit cell, you do the nanoindentation only once and you don't have problems. Okay, there is a contact area, but since the indenter is 5 nanometers, it's really big. So only with one simulation, it is enough. So the error bars are really small. But since now we have the mixture complexity for the nickel iron 20% and 50%, it is not enough only to perform one MD simulations. So we decide to perform around 20. It's enough for good statistics in the results. And these error bars is the maximum hardness that we have from out of these 20 MD simulations, and this is the minimum. So the hardness for 20% and 50% are into the error bars, and it's the same for the experiments. So now we have here for chromium, and we also perform 20 MD simulations. So this is a qualitative good agreement between the experiments and the MD simulations. Is the internet okay? Because sometimes it's failing here in my house. Is Chelsea is okay?
All good. Yeah, all good.
Okay, thank you. So what is the reason that we have this increase of the hardness value for the materials? What is happening? They are seeing this in the experiments, and we are also seeing this in the MD simulations. So what is the reason? So the reason is that here we are calculating the dislocation nucleated and propagated in the sample due to the nanoindentation test, due to the loading process. So when you're doing the nanoindentation, some of the atoms are making room for the indenter, and they are going up of the surface. So these atoms that they are going up of the surface, these are the pileups. They are amorphous, and the geometry of these atoms is very amorphous. So then inside you are creating interstitials, and this cumulative interstitials or linear interstitials, they are going to have some orientation according to the Borger vectors that they have, and also you are creating vacancies. So all these process that you are creating when you are pushing with this indenter, the result is the dislocations, nucleated and propagated. So when you are doing deeper, the dislocations are propagating, as you can see here. I'm going to show a movie about this, but I want to discuss first here what is the correspondence between the dislocation density here as a function of the indenter displacement for nickel. For nickel here, even you can see that in the elastic part, you only see the Shockley partials. But then when you are going to the plastic deformation transition, you can start nucleated other type of dislocations. So then you are going to find the Hirt and the Frank junctions. Here is the junction, and I'm going to show how the junctions are. For nickel, when you are doing an indentation at 1 nanometer depth, you have an embryonic prismatic dislocation loop that then when you are going deeper, it forms the prismatic dislocation loop. Then when you are going even deeper and deeper, you start seeing this pyramid, the so-called pyramidal shaped stacking fold tetrahedron. It looks like a pyramid, but maybe some people can say, no, it's not a pyramid, but it's a stacking fold tetrahedron. And they are formed mainly by the Hirt junctions. Then when you are going even deeper, you can nucleate more. And then you are doing the unloading process, and some of the prismatic dislocation loops, because of the mobility, they are and the recovery of the material, they are coming back and being absorbed by the surface when the indenter tip is coming back and doing the unloading process. So you are going to see all of this, but I also want to show you that here in the dislocation density graph as a function in the indenter displacement, you can see here the nucleation of the prismatic dislocation loop, another one, and then the nucleation of the stacking fold. Then you have another prismatic dislocation loop, and then you have another stacking fold tetrahedron. So what is happening when you are adding iron? Well, when you are adding 50% of iron, now the mobility of these defects is slower because of the presence of iron. And even you have 1 nanometer and there is no embryonic prismatic dislocation loop, but then there are 2 prismatic dislocation loops already formed, but they go deeper really slow, that even the pyramidal shape stacking fold tetrahedron is not formed at 4.5 nanometers, and here for nickel already you have 2, and then you are doing the unloading process and there is nothing. This is also observed here in the dislocation density as a function in the indenter displacement, that you have the formation of the prismatic dislocation loops, but then there is nothing, and you have the stacking fold tetrahedron here at 4.5. And what is happening when you have nickel, iron, chromium 20%? This is the maximum indentation depth, and there is no propagation of of the dislocations. Even there is nothing formed, no prismatic dislocation loops, nothing. So this is the reason. This is one of the reasons why the hardness value for nickel, iron, chromium is higher than for nickel, because you can compare here. The nickel is nothing, and you are going reaching the same depth, and nickel already present these defects, and chromium is like, you know, it's like you already reached 2 nanometers for nickel, so it's really tough material. So this is one of the movies that we have for nickel. This is the thing that I was talking about. You have the nucleation, then you have the slip system in the 111 slip system, and then because it's an FCC material, then you have the nucleation of the prismatic dislocation loop, and then here you can see the interaction between the prismatic dislocation loops and then the formation of the stacking fault tetrahedron. This has the here junctions, these yellow lines. Then you also can see here this triangle that is the only stacking fault tetrahedron. And then here you can see the tip depth, and then the time of the simulation. This is only for nickel, and then we already reached the unloading process. So what is happening when you have 50% of iron in the material? So again, it is the dislocations are being nucleated, then it is more difficult to propagate for them. And it's even more difficult to form the stacking fault tetrahedron. It's even more difficult. I already reached 5 nanometers of the indentation for loading. There it goes, the dislocation, the unloading process. So the tip is going up, and you have more time, and you see the difference. The mobility for the prismatic dislocation loop, they are really slow. There is one stacking fault tetrahedron form, really small there, and the simulation is done. So we are talking about these dislocations, these characteristics of the material, but what about the experimentalist researchers? They are also finding this kind of defects in the material? Yes. So here we have the TEM image that the experimentalists can obtain from the samples. And here they can identify this stacking fault tetrahedron here for nickel. This TEM image is for nickel. Here it is. And this is another prismatic dislocation loop and another prismatic dislocation loop. So all of them coexist in the same plastic region. Yeah, in good agreement with the MD simulations, all of them coexist in the plastic region because it's an FCC and because of the crystal orientation. But what about when you add 50% of iron? Well, then the story change, and then here, to me, this is another stacking fault, but maybe we need to discuss more a little bit. But here you have another one. This is for nickel iron 50%, and then you have more dislocation loops here. But with this TEM image, you don't have too many prismatic dislocation loops. So again, this is a qualitative good agreement between the MD simulations and the experiments. What else can we do with the MD simulations and the experiments? I was talking about the pile-ups and also the slip systems. Now for nickel, this is how it looks, the pile-up for the pile-ups for nickel when you're reaching the maximum indentation depth. And in this line, I'm making sure that this is the slip system. And then you can see the geometry of the pile-ups. So all of these are the atoms that are accumulated above the surface. And this is an image that is obtained by SEM. It is really fresh. Thank you so much for the image. And here, again, we can see this correspondence. Here, I don't know, to me, these are the pile-ups. This is the geometry of the pile-ups, here, 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 here. And you have it here, here, here. This is the indentation, here, here, here. You have the other family here, and they are here. You have the correspondence here, and you have another here, and another here. So this needs to be discussed more, but to me, this is another good agreement between the experiment and the MD simulations and it follows the characteristics of the FCC material oriented in the 001 direction. So now we need to see the strain, the atomic strain, by computing the von Mises strain and for each atom. So when we are doing the maximum indentation depth, we notice that the maximum strain, oh, sorry, this is inverse. I apologize for this, because the maximum strain is here underneath the tip. And then you have the other atomic distribution for the von Mises strain. And for the stress, you also have the same distribution underneath the tip. You have the maximum stress. And then what is happening when you are adding 50% of iron? For 50% of iron, the geometry of the pileups change it. And then also the strain, you have the maximum in the depth. And you can see that here, you have the other dislocation and not present for this tip, and also for the stress. And now, what is happening when you have 20% of chromium? The pileups are not, and are even not formed. You only have the clouds of the atoms formed around the indentation, the tip, where the mark of the spherical indentation tip is. And then you have here the strain, where the maximum strain is underneath the tip, and also for the shape of the stress, or the von Mises stress for the maximum indentation depth, that is similar like the one in nickel when you reach 2 nanometers, only that it is like scaled to 5 nanometers. This is to me, this is something that it's really nice to understand how the material has it is harder than the other material. This is really nice. So my concluding remarks is that the combining experimental and numerical study has been conducted. We described the evolution in single crystalline SP-CSAs using nanoindentation and MD simulation, experiments of nanoindentations and MD simulations. The stack-fold tetrahedron and interstitial prismatic dislocation loops coexist in the same region in good agreement with the TEM images, the one observed in the MD simulations. We also suggest that the defect density increases and defect size decreases as a function of the increase of the iron concentration and chromium concentration. And the present study validates experimentally obtained TEM data. And I think I reached the end of my talk, and probably is in good time. And I would like to thank everybody for listening to me.
Well, thank you, Javier, for the beautiful talk. You really improved very much the way of presentations. Yes,
thank you.
And it's impressive that you were able to treat by atomistic simulations processes that were considered to be only in domain of experiments. So I'm really impressed with the results that you're getting and the good comparison of the experiment. So I have two questions, if you allow me. I mean, before others start,
yes,
because
of course,
I already
yeah.
talked. So one question is something that I also taught you always, and this is that microdynamics is as good as potentials are good. Otherwise, if potentials are not good, you can easily be moved to a parallel universe. Okay, but we are interested in processes.
Yes, I know this.
In this, yes. So, what was the potentials that we're using?
I'm using the potential developed by. By Choi, sorry, it's these potentials is MEEM and second modified, second nearest neighbor modified MEEM potentials. They are developed by Choi et al. I didn't put the reference, I'm sorry, but they are well tested. All of us spend, well, Rene and I spent practically 2 months testing the potentials, and everything fits.
Okay.
So,
okay, very good. And my second question was concerning in the statistics that you were collecting. So you said you found that 20 MD simulations were giving you good statistics of the processes. So when you say 20 simulations, what do you mean? What did you change between the simulations? Initial conditions or something else?
No. Here, you can see that in the experiments, they are doing one nanoindentation here in this location. So it's practically like, well, okay. So you have the surface here, and then you are doing the nanoindentation in this position. Then you move the indenter, and you do again the nanoindentation. You move it to another position, and you do the nanoindentation. They are doing this in the experiments.
Okay, so it was equivalent to bombarding with the particles.
Exactly,
okay?
exactly.
Where we were doing thousands of trajectories. Okay, so
yeah, yes, exactly.
So the 20, are you sure 20 was enough?
Yes, I'm sure.
Okay, all right, thank you. So other people can ask.
Thank you, Professor.
Javier, let me jump in with maybe a couple of quick questions. So I guess I'm interested in the finite size effects, because I mean, this is one of the really, I think, challenging models for dislocations is they propagate a really long way, and you of course accumulate pressure. And how do you understand that convergence with respect to the size of your simulation domain?
Well, we perform many tests. So you have the radius of the indenter tip, which is 5 nanometers, and we also test the size of the numerical cell, and we also have the pressure. So that's the reason we define different sections for the sample and also the vacuum, and then this periodicity. We notice that the dislocations need to be inside or only around the tip in the so-called plastic deformation region. So you're right. When we have this side effects, you can see it here that the pH, the load displacement curves, they don't fit to the Hertz fitting, and also they are doing something random because of this pressure, the extra pressure that you have. Once we have this Hertz fitting, we are sure that the MD simulation is well performed.
Okay, that's a very nice diagnostic. And I guess kind of related to this, there was something I didn't understand in the experiment. Is the tip experimentally moving at a constant velocity, or are they increasing the force and seeing?
No. Lucas, could you please help me with this?
Yes. So
Thank you.
no problem. You can hear me.
Yes.
So the velocity of the indenter is constant, and we are increasing depth with each indentation. So here, this load displacement curve actually represent 10 indentations, 10 or 11, something like that, made in the same spot with increasing force. And then Javier was fitting the elastic part and the unloading. Yeah, but of course we can do single indentations in one individual location, as was presented by Javier slide before, or 2 slides before. Yeah.
Okay, that helps a lot. That was a misunderstanding on my side. Thank you.
No problem.
And then
thank you, Lucas.
Then also, not being a material scientist, the TEM images were really interesting. They showed sort of like almost a pyramidal shape left. And I initially had the impression that the indenter experimentally was like a sharp tip. But is that just because of the cubic structure of the material that it makes?
What we can, this is not in situ TEM. This is TEM recorded after the experiment. So the structure is already plastically deformed. What Javier said is that we see that there is a very nice correlation between the amount of the defects generated and the size. You can see that the C figure, which represents 50% iron, has more defects, but they are smaller in size. And this is exactly the same what Javier got from his calculations on the density dislocations.
Dislocation density.
Exactly. Yeah. So, but this is not in situ TM. This is post-mortem analysis. But still, and of course we see that the stacking faulty dihedra and prismatic dislocation loops, they do exist. They coexist. But we are able to study, of course, a certain volume of the material. Yeah.
Okay, good. Thank you both very much indeed.
Thank you.
Something?
Yes.
Hi. So really nice talk. This is actually very exciting for me because this has been a topic of interest. Could you go back to the concluding? I want back to the concluding slide. I want to have this in front of me when I ask my question. Because when I was studying, so it's when you have the alloy, you're seeing more smaller defects or fewer larger defects?
More. They are again your question. Sorry.
Okay, so the defect density increases and the size decreases.
Yes, exactly. Right?
Okay, so something, I was actually looking at the same material system, and something that I found really interesting is that, so everyone always talks about like sluggish vacancy diffusion and stuff like that. But something that I observed, and I've been really wondering how this affects larger defects like these stacking fault tetrahedrons, is that the distortions in the lattice create both barriers to motion and also shortcuts to motion. They're like these high mobility tracks that I found that vacancies will zoom between. And I've been really wondering if that makes any effect on like defect consolidation, or if it's actually just making these small isolated clusters.
Well, not here, not here, because this is low temperature. But
as a start,
for high temperature, you're right. We saw it for molybdenum at high temperature. We saw that the lattice distortion is moving faster. So you have the defects nucleated and then they are moving. So you're right. This is the reason of the thermal mechanical stability for molybdenum at high temperatures. Yes.
Okay. Oh, thank you. Really interesting.
No, thank you.
Javier, how many particles did you have in your sample?
More or less 3.1 million.
Okay. So what kind of computing power did you use?
I'm using the cluster of NCBJ. And sometimes I'm using the cluster of Stony Brook.
Okay. So was there anything like a time step in your calculation?
Yes, it's 0.000105 femtoseconds.
How many zeros? 0.05 femtoseconds. Is it what you meant?
Yes, exactly.
So it's really, really short. Why did you need such a short step?
Because of the nucleation of the dislocation nucleation. Because if you are doing it with a time step really big, the dislocation are only they don't look good. So this is only like stochastic, and you cannot see the formation of the dislocation and the interaction between the prismatic dislocation loops. It needs to be slow to see the propagation of the dislocations. But,
and how many steps are you accumulating?
So it's 125 picoseconds million.
Yeah, okay. It's a huge calculation.
Yeah. Yeah, but you show me how to do it. So thank you so much.
Okay, okay.
I think more.
Is there any more questions? So, okay, if not,
I may just comment that it's been a nice journey with Javier for a couple of months. It took me some time to understand what he's talking to me.
Well, it was really nice that we have this talk.
But yeah, it's starting to really getting interesting, and we will continue with different compositions with different materials. And then the approach is we already sent our work to a couple of professors. They are reviewing it, but it will be growing, that's for sure. So thanks again, Javier, for your work and for your time.
Thank you for the motivation and for your help. Wow.
That's the beginning.
Thank you, Lucas. And believe me, he will improve his Polish in time.
He will have to. I'm sending him from time to time some articles in Polish, and we are talking to him in Polish when drinking coffee. So
I heard he knows at least one word. He said "tak."
Tak, that's perfect. Yeah.
Thank you.
Okay. I think we can close this session.
Yeah.
Thank you very much.
Thank you so much, Javier.
Thank you.
It was a pleasure.
Thank you very much,
Sept. Thank you,
Javier.